Hi everyone. We're back for our last video on linear equations review. So in our last video we graphed two lines. Now we're going to talk about systems of equations, which is related to that idea. Oops, sorry, I have a little mouse issues here. So let me scoot this up. And we're going to talk about solutions to a system of equations and what that means. So a system of linear equations consists of two or more linear equations. In this class, we're only ever going to deal with two equations in our linear systems, but as you progress through math and your abilities in this subject grow, you'll start to be able to handle bigger and bigger systems. The example that we did in our last video actually constitutes a system of two linear equations. We graphed them both on the same graph. A point, or set of points, that all the equations in the system have in common is called a solution to the system of equations. So when we have a system of linear equations, we are looking for the points that they have in common. When we graph those lines, the solution or solutions are where the lines cross. Whoops, that's not how you spell cross. Where they cross, or using more mathy words, where they intersect. Or in some cases where they overlap, because they may overlap in more than one point. Before we move on to our three possible cases, let's go back to that system we graphed in our last video and identify that solution. Looking at this system from our last example, it looks like if I were able to draw those lines accurately, they would intersect right here. That's where those points are crossing. And that looks like that is at 2, 2. So the solution to the system of equations y equals 3x minus 4 and y equals minus x plus 4 is the point 2, 2. What that means is that's the only point in the entire coordinate plane that makes both of those equations true at the same time. And we can check. If I were to go to that first equation and plug in 2 for x, 3 times 2 is 6, and 6 minus 4 is 2. So putting an input of 2 gives us an output of 2, which is exactly what this ordered pair shows us. If we do the same for the second equation, I plug in 2 for x, minus 2 plus 4 is plus 2, which is exactly our output. So input of 2, output of 2. So that point makes both equations true. So let's go back down to this three possible cases section. When we're graphing two or more lines, we can have three cases. The first is the one we just saw. The lines cross exactly once. Whoops, that's not how you spell once. So there is exactly one solution, one ordered pair that's true for both equations. And we can see that right here, case 1. The red line, the blue line cross exactly once at the point minus 2, 1. The second case, which I'll scroll down to in a minute, is that the lines never cross. They never touch. And in that case, there are 0 solutions. So you would write as your answer, no solution. It doesn't happen often, but it's absolutely possible, and that is a valid answer. So let's take a look at that. Case 2 down here is a no solution case. There is no points in common for this graph. And I see something kind of cool. I know when lines don't cross, we would call these parallel lines. So anytime I see parallel lines in a graph, I know my answer is no solution. But also, look at that x term. For both of those equations, that slope is positive 1. And up here, same thing, positive x, our slope must be positive 1. So when you have cases where there's no solution, those equations will have the same slope, but different y-intercepts. One crosses down here at 0, minus 2. One crosses way up here at 0, 3. But because they go up and over the same amount, they never intersect. The third case is the weirdest. The third case is when the lines overlap. You graph them and they fill up the exact same space in the coordinate plane. And in that case, every point on those lines is in common. And because the lines go on forever, we would say there are infinitely many solutions. And you'll see here in this example, one of our equations is written in slope-intercept form, y equals 2x plus 1. One of them is written in standard form, minus 4x plus 2y equals 2. And I want to take just a second, you don't have to watch this, but if you're interested, I want to take a second and convert that to slope-intercept form, because I think we're going to see something cool. I know for slope-intercept form, I want to get y by itself. So I'm going to draw this dotted line down the middle, and we're going to solve this equation for y. In order to get y by itself, the first thing I have to undo is the thing being added or subtracted, which is this 4x. And because it's being subtracted, I'm going to add it to both sides. When I do that, on the left, minus 4x plus 4x, that's a zero pair. Those go away. So I'm left with 2y. On the right, one term has an x in it, one term is a constant. I know that I can't combine those, so I'm just going to write this as 4x plus 2. You could also write it as 2 plus 4x, but I know in slope-intercept form I want the x in front. So in order to get y by itself, there's one more thing I have to move, and that's the 2. And right now it's being multiplied, so I'm going to divide by 2. But if I do that on the left, I have to do that for everything on the right as well. So let's go ahead and cancel for, get a different color, make it a little more clear here. For the 2's, those are going to cancel. On the other side, those are going to cancel, 1 and 1. The 4 and the 2 are going to reduce and leave me 1 and 2. So this has left me a much prettier equation. On the left, I've got just y. On the right, I've got a 2 and an x plus and then 1. This equation is this equation. The reason that they're the same line on the graph is because if I rewrite that standard form, it produces the same slope-intercept form. Same slope, same intercept, infinitely many solutions. Okay, hopefully that helped you out. Hopefully we have an understanding of what these graphs might look like when we're graphing systems of equations. Next time I see you, we'll actually practice solving systems of equations by graphing.